Hello everyone. I will now begin the 7th video on pitch geometry. In the previous 6 videos on pitch motion, we examined front-wheel drive, rear-wheel drive, all-wheel drive, and braking. Regarding pitch motion in relation to braking, we have analyzed cases where braking force acts on all 4 wheels. However, we have not analyzed cases where braking force acts only on the front wheels or only on the rear wheels. Front-wheel braking has a force transmission path similar to rear-wheel drive, and rear-wheel braking has a force transmission path similar to front-wheel drive. In this video, we will examine dive during pitch motion when braking force is applied to the front wheels equipped with outboard brakes. Unless otherwise noted, everything discussed in this video applies to cases where only the front wheels are braked without rear braking, and the braking device is an outboard brake. In this video, we will refer to both driving acceleration and braking deceleration as acceleration and distinguish between the two by the sign of the acceleration. If the acceleration is positive, it is driving; if it is negative, it is braking; and if it is zero, it is constant speed driving or static state. Acceleration and braking forces also use the same symbol, and the two are distinguished by the sign of the force. If the sign of the force is positive, it is driving force; if it is negative, it is braking force. I will now introduce the contents of this video. In this video, I will explain how to analyze pitch geometry when braking forces are applied to a front-wheel braking vehicle. First, I will explain how to predict the pitch motion of a vehicle that brakes only the front wheels, without rear-wheel braking. I will explain the direction of forces acting through the links and the springs, and then explain the direction of the vertical component of the force when these link and spring forces act simultaneously. Subsequently, I will explain how to analyze pitch motion and vehicle attitude using mathematical methods. I will explain how to derive the force-moment equilibrium equations when a braking force acts on the pitch geometry, and how to determine the conditions for zero dive and zero pitch angle. Finally, I will explain the effect of virtual reaction points on pitch motion during front-wheel braking. Related topics will be the forces acting on the springs and links that vary depending on the position of the virtual reaction point, and explain the dive and pitch angles that change accordingly. I have a quiz for you. In a front-wheel braking vehicle, which statement is correct when the virtual reaction point is located between the dive zero line and the pitch angle zero line? Number 1. In absolute value, the link force is smaller than the spring force. Number 2. In absolute value, the link force and the spring force are equal. Number 3. The front ride height becomes smaller than in the static state. Number 4. The rear ride height becomes smaller than in the static state. Number 5. The front ride height is larger than the rear ride height. Number 6. The front ride height is smaller than the rear ride height. Please select the one correct answer from these 6. Regarding the sign and direction of the vertical dynamic load on the link and spring, I will explain using the front-wheel braking force, shown in this figure, as an example. When the virtual reaction point exists between the road surface and the dive zero line, both of these forces are directed vertically downward and act as compressive forces on the spring and link. The dive zero line will be explained later. For ease of understanding, I will define the compressive force as negative. If each of these two forces has a negative value, it is compression, and if each of them have a positive value, it is tension. For example, if delta WZF itself is positive, minus delta WZF is negative, so it is compression. If delta WZF itself is negative, minus delta WZF is positive, so it is tension. In the case of front-wheel braking, if the virtual reaction point is below the road surface, delta FZF is negative. Therefore, minus delta FZF in the figure is positive and acts as a tension force on the link. If the virtual reaction point is above the dive zero line, delta WZF is negative. Therefore, the minus delta WZF in the figure is positive and acts as a force that tensions the spring. This will be explained with a figure later on. The amount of vertical dynamic load transferred during braking can be expressed by equation 1. Additionally, since the sum of the spring vertical dynamic load and the link vertical dynamic load is equal to the amount of total vertical dynamic load transfer, this can be expressed by equation 2. Meanwhile, we let eta F represent the fraction of the total vertical load transfer developed on the front suspension links. This can be expressed as equation 3. Therefore, the vertical dynamic load acting on the link can be expressed as equation 4. From equations 2 and 4, the spring vertical dynamic load, delta WZF, can be expressed as equation 5. The magnitude and direction of the vertical dynamic load acting on the spring, WZF, are determined according to equation 2, once the link force, delta FZF, of the suspension with the brake wheel is determined. Since the expressions of vertical dynamic load acting on a spring and a vertical dynamic load acting on a link make it difficult to understand the direction of the forces, we will refer to the force, shown in this figure, as compressive force and the opposite case as tension force. Compressive force is a force that increases ground reaction force, while tension force is a force that decreases ground reaction force. In springs and links, the representative symbol for compression is indicated by a vertical downward arrow, and the representative symbol for tension is indicated by a vertical upward arrow. Although the braking force FXF, acting horizontally on the road surface, acts in the negative x-axis direction, to use the same equation for acceleration and braking, we will use it without a minus sign, in the same manner as acceleration AX. This will also be explained later. Let's analyze the vertical components of the force on the links and springs during front wheel braking. The first and most important aspect of analyzing pitch motion is analyzing the forces acting on the suspension links where the braking wheel is located. For example, when braking force is applied to the front wheels but not to the rear wheels, to analyze the pitch motion, we must first calculate the force, delta FZF, acting on the front suspension links where the braking force is applied. The amount of total vertical dynamic load transfer remains constant once the acceleration AX is fixed and can be expressed as equation 1. Since the springs and suspension links are the only paths through which the load is transferred, all forces are transferred through these two paths. In the front suspension with the braking wheel, the vertical dynamic load transfer is equal to the sum of the forces on the front suspension links minus delta FZF and the front spring force minus delta WZF. Thus, it can be expressed as equation 2. In equation 2, AX represents the braking deceleration and has a negative value. Therefore, in equation 2, minus delta WZF and minus FZF both have a vertically downward direction and act as forces that compress the springs and links. Since no braking force acts on the rear suspension, the amount of vertical dynamic load transfer through the rear suspension links is 0. Therefore, the amount of vertical dynamic load transfer by the rear suspension can be expressed as equation 6 using the force that tensions the spring, delta WZR. Since the acceleration AX has a negative value, the vertical dynamic load acting on the rear spring, delta WZR, has a positive value and acts vertically upward to tension the rear spring. Once the magnitude of the braking deceleration is determined, the magnitude of the vertical dynamic load transfer is determined, and the ground reaction force at the front wheels increases by the amount of the vertical dynamic load transfer, while the ground reaction force at the rear wheels decreases by the amount of the vertical dynamic load transfer. If acceleration AX is constant, the increase in front ground reaction force must also have a constant value. Therefore, the sum of the increase in front spring force and the increase in front suspension link force must be equal in magnitude and opposite in direction to the increase in front ground reaction force. Consequently, since the vertical dynamic load transfer is constant if the force acting on the front links in the front suspension increases, the force acting on the front spring decreases, and conversely, if the force acting on the front links decreases, the force acting on the front spring increases. However, in the rear suspension, since no force acts on the rear suspension links, the force acting on the rear suspension links is zero, and force acts only on the rear spring. Let's examine the conditions for zero dive and zero pitch angle during front wheel braking. Since the vertical dynamic load transfer, the increase in front ground reaction force and the decrease in rear ground reaction force are determined by the laws of physics. As long as acceleration ax is constant, they hold constant values regardless of the geometry of the suspension links. The condition for zero dive during braking is that the front spring displacement becomes zero. To make the front spring displacement zero, one must make the vertical dynamic load acting on the front spring, delta WZF, zero. By changing the geometry of the front suspension links to alter the position of the front virtual reaction point SF, the magnitude of the resultant force acting on the front suspension links can be changed. Consequently, the magnitude of the force acting on the spring changes and the front ride height changes. In the rear suspension, since no force acts on the links, once acceleration ax is determined, the rear spring displacement and rear ride height are fixed and cannot be changed. Therefore, to make the pitch angle zero, the front ride height must be raised to the level of the rear ride height. Remember that acceleration ax has a negative value during braking. What requires attention here is the direction of action of delta FZF. To explain this, we introduced the eta F, which represents the fraction of the total vertical dynamic load transfer developed on the front suspension links, as shown in equation 4. The front spring force, delta WZF, can be expressed as shown in equation 5, using the fraction eta F depending on the position of the virtual reaction point. The direction of action of the force, delta FZF, can be downward or upward. The direction and magnitude of the force acting on the front spring, delta WZF, vary depending on the direction and magnitude of the force on the front suspension links, delta FZF. Let us examine the principle behind this with a figure. Let's examine the relationship between the link and spring forces based on the location of the virtual reaction point. The method for determining the pitch angle zero line and the dive zero line in the figure will be explained later. The pitch angle zero line can be expressed as equation 7, and when the front spring stiffness and the rear spring stiffness are equal, equation 7 can be expressed as equation 8. Region 1 represents the case where the virtual reaction point SF lies in the region below the horizontal line, connecting the front tire's road contact center, point A, and the rear tire's road contact center, point B. This is indicated in light yellow. In this case, the vertical force compressing the spring is greater than the resultant vertical force tensioning the links based on absolute value. In this case, eta F is negative, meaning it is less than 0. Line 2 represents the case where the virtual reaction point SF lies on the horizontal line, connecting the front tire's road contact center, point A, and the rear tire's road contact center, point B. In this case, the resultant vertical force of the links is 0, and only a vertical force compressing the spring exists. In this case, eta F is 0. Region 3 represents the case where the virtual reaction point SF lies in the region between line AB and line AG, indicated in light green. In the figure, point G is the point where a horizontal line parallel to the ground, passing through the center of gravity, CG, intersects the vertical line, passing through the rear tire contact point, B. In this case, a vertical force compressing the front spring and a vertical force compressing the front suspension links are generated, both acting vertically downward. In this case, eta F is greater than 0 and less than 1. Most commercially available vehicles have a virtual reaction point in region 3. Region 4 represents the case where the virtual reaction point SF lies on line AG. In this case, the vertical resultant force of the front links is equal in magnitude and opposite in direction to the vertical dynamic load transfer, so the force acting on the spring becomes 0, and the force acting on the front links supports the entire vertical dynamic load of the vehicle. Therefore, brake dive is 0. In this case, the value of eta F is 1. Let's examine the relationship between link and spring forces based on the location of the remaining virtual reaction point, SF. Figure 5 illustrates the case where the virtual reaction point, SF, exists between the dive 0 line, AG, and the pitch angle 0 line, AS, and is shown in light red. In the figure, point S is the point where a horizontal line parallel to the ground, passing through point U, which is at twice the height of the center of gravity, CG, intersects the vertical line, passing through the rear tire contact point, B. When the virtual reaction point exists in this region, the force compressing the links acts vertically downward, while the force tensioning the spring acts vertically upward. In absolute terms, the force of the links is greater than the spring force. In this case, the value of eta F is greater than 1 and less than 2. If the virtual reaction point exists in this region, the front ride height increases. However, since the front ride height remains lower than the rear ride height, the vehicle stance is lower at the front and higher at the rear. Figure 6 illustrates the case where the virtual reaction point, SF, lies on the pitch angle 0 line, AS. In this case, the vertical resultant force compressing the front links is twice the vertical dynamic load transfer, and the force tensioning the front springs is equal to the vertical dynamic load transfer. Since this force is equal to the force tensioning the rear springs, the same displacement occurs in both the front and rear springs, and consequently, the pitch angle becomes 0. In this case, the value of eta F is 2. Figure 7 illustrates the case where the virtual reaction point, SF, is located in the region above the pitch angle 0 line, AS. The front ride height is greater than the rear ride height, and the vehicle stance is higher at the front and lower at the rear. A force greater than the vertical dynamic load transfer tensions the springs, and a force more than twice the vertical dynamic load transfer compresses the links. In this case, the value of eta F is greater than 2. Let us analyze all the contents explained above at once. This figure simultaneously illustrates the vertical force of the spring and the resultant vertical force of the links acting within the regions of the 7 virtual reaction points described earlier. As explained, when a vehicle brakes with a constant deceleration AX, the vertical dynamic load transfer of a front-wheel brake vehicle, derived from Newton's second law, is represented by equation C. It has a constant value that does not vary, depending on the type of suspension and braking system. Therefore, when the vertical force acting on the spring and the resultant vertical force of the links are added together, the value represented by equation C must be the same in any case. Equation C represents the resultant vertical force acting on the spring and links, not the ground reaction force. By using eta F, the ratio of the resultant vertical force of the suspension links to the vertical dynamic load transfer, the spring force and the resultant vertical force of the links for the 7 virtual reaction points can be easily analyzed. Point 1 indicates that if the virtual reaction point exists below the road surface, eta F is negative, meaning that the force compressing the spring is greater than the force tensions the links. Number 2 indicates that if the virtual reaction point is on the road surface, eta F is 0, meaning only the force compressing the spring acts and the force acting on the links is 0. Number 3 indicates that if the virtual reaction point is between the road surface and the dive 0 line, eta F is greater than 0 and less than 1, meaning both the vertical force compressing the spring and the vertical resultant force compressing the links are vertically downward. Number 4 indicates that if the virtual reaction point is on the dive 0 line, eta F is 1, meaning that the vertical force acting on the spring is eliminated and only the vertical resultant force compressing the links acts. In this case, the dive becomes 0. Number 5 indicates that if the virtual reaction point is between the dive 0 line and the pitch angle 0 line, eta F is greater than 1 and less than 2, meaning that the vertical force tensioning the spring acts upward and the vertical resultant force compressing the links is vertically downward. Number 6 indicates that if the virtual reaction point lies on the pitch angle 0 line, eta F is 2, meaning that in absolute value, the resultant vertical force compressing the links acts twice as large as the vertical force tensing the spring. In this case, since the same force acts in the same direction on the front and rear springs, the pitch angle becomes 0. Number 7 indicates that if the virtual reaction point lies above the pitch angle 0 line, the eta F is greater than 2, meaning that in absolute value, the resultant vertical force compressing the links is more than twice as large as the vertical force tensioning the spring. In this region, the front ride height is greater than the rear ride height. Let's analyze the vertical dynamic loads acting on the suspension links during front wheel braking. The link forces for pitch motion during front wheel braking are similar to the link forces for pitch motion during rear wheel acceleration. Forces acting on the links do not occur in suspensions without drive or brake wheels. They occur only in suspensions with drive or brake wheels. This simple fact is very important in the analysis of pitch motion. We have previously analyzed the vertical components of the forces acting on the suspension links during rear wheel acceleration as explained in the previous video, E0087, Pitch Geometry Part 1. This figure illustrates the case where the virtual reaction point is located in the region between the road surface and the dive 0 line. Since all forces shown here are dynamic loads, they are all 0 at constant speed or at a static state. When the front wheel braking force Fxf is applied, the resultant vertical force acting on the front suspension links, delta Fzf, can be expressed as equation 9 using the vertical dynamic load acting on the front suspension upper link, F1z, and the vertical dynamic load acting on the suspension lower link, F2z, and is indicated by the green arrow in the figure. The suspension link vertical dynamic load, delta Fzf, acts vertically downward and is a force that compresses the links, thereby increasing the ground reaction force. The delta Fzf represents the ground reaction force that increases due to the suspension link vertical dynamic load minus delta Fzf. The suspension link vertical dynamic load minus delta Fzf is the vertical dynamic load transmitted through the links out of the total vertical dynamic load transfer, expressed by equation 2. Next, let's look at the vertical dynamic load transmitted through the springs. Let's analyze the vertical dynamic load acting on the springs. First, let's examine the load transfer through the springs in the case of a front suspension with brake wheels. In a suspension with brake wheels, the transfer paths can be divided into two. The first is the load transfer through the suspension links explained earlier, and the second is the load transfer through the springs explained here. In the case of a suspension with brake wheels, the sum of these two load transfers represents the total vertical dynamic load transfer of the vehicle. In this figure, we exclude load transfer through the suspension links and consider only load transfer through the springs. The magnitude of the load transfer through the springs depends on the center of gravity, CG, and the location of the virtual reaction point, SF. This will be explained in detail later. In most vehicles currently on the market, the vertical dynamic load transferred through the spring minus delta WZF acts downwards the front of the vehicle and compresses the springs. As a result, the front ride height decreases by delta F. Here, the displacement delta F has a positive value during a bump and a negative value during a rebound. Therefore, the front wheel ground reaction force, delta WZF, has a positive value and acts in the vertically upward direction. The vertical dynamic load, delta WZF, is the amount of vertical dynamic load transferred through the front springs when a braking force FXF is generated. As with the rear wheel drive case, analyzed in the previous video, the ground reaction force, delta WZF, here is the ground reaction force generated solely through the springs, without passing through the suspension links. Due to the action of the vertical dynamic load, it has a value of 0 in a static state. If the ground reaction force, delta WZF, for the vertical dynamic load acting on the springs is positive, it means that the total vertical load increases due to load transfer, and if it is negative, it means that the total vertical load decreases due to load transfer. In the example shown in this figure, the front wheel ground reaction force, delta WZF, indicates that the front wheel vertical load increases because load transfer occurs through the springs. Let us analyze the vertical components of the suspension links and the springs that we have analyzed so far. We will analyze the pitch motion of the vehicle when a braking force, FXF, is applied and acceleration, AX, occurs. When the vehicle is braking with acceleration AX, the total vertical dynamic load of the vehicle, that is, the load transfer from the rear to the front, can be calculated using Newton's second law, the height of the center of gravity, CG, and the wheelbase. Regardless of the suspension links or springs, the total vertical dynamic load transfer of the vehicle has a constant value corresponding to the braking force, FXF, once it is determined. When vertical dynamic loads are generated by vehicle braking, the vertical load on the front wheels increases by the vertical dynamic load, and the vertical load acting on the rear wheels decreases by the same amount. These vertical dynamic loads represent the load transfer amount from the rear to the front. It is important to note here that, in a front suspension with a brake wheel, vertical dynamic load transfer occurs through both the spring and the link, whereas in a rear suspension without a brake wheel, it occurs only through the spring. In this figure, delta WZF indicates that the vertical dynamic load acting through the spring acts vertically downward, compressing the spring, and similarly, delta FZF indicates that the vertical dynamic load acting through the links acts vertically downward, compressing the links. As previously discussed, in a vehicle with suspension geometry, like the example in this figure, when braking force is applied to the front wheels, the vertical component of the force, acting on the links of the front axle suspension upper and lower arms, acts vertically downward, and the vertical component of the force, acting on the spring, also acts vertically downward. Therefore, in this case, the vertical dynamic load, acting on the front wheels, is negative, and it can be seen that the direction of force application is vertically downward, compressing the springs and links. The ground reaction force relative to the total vertical dynamic load transfer is equal to the sum of the load transfer through the springs, delta WZF, and the load transfer through the suspension links, delta FZF. At the front wheels, the vertical load increases by the amount of these vertical dynamic load transfers. Meanwhile, in the rear wheels that do not generate braking force, the vertical dynamic load is transmitted to the ground as a force that tensions the springs, so the vertical load on the rear wheels is reduced. Since there is no load transfer through the rear suspension links, the total load transfer from the rear to the front acts through the springs, and this magnitude is equal to the vertical dynamic load of the entire vehicle calculated by Newton's second law, and acts as a force that tensions the springs. In the previous video, E0001, Vehicle Dynamics, Load Transfer, we studied the forces generated in an accelerating vehicle. Among these contents, we will review the load transfer for a vehicle subjected to acceleration AX. All forces shown in the figure and equations FXF, FZF, FXR, and FZR all represent the combined force of the left and right wheels. From the equilibrium of forces acting horizontally on the vehicle, equation 10 can be derived, and from the equilibrium of forces acting vertically, equation 11 can be derived. Additionally, equation 12 can be obtained from the moment equilibrium of all forces generated during acceleration around the vehicle's center of gravity, CG. From these three equations, the vertical force, FZF, acting on the front wheels during acceleration can be calculated as equation 13, and the force, FZR, acting on the rear wheels can be calculated as equation 14. The first term on the right-hand side of equation 13 represents the load acting on the front wheels at static state or constant speed, and the second term represents the load resulting from the decrease in weight of the front wheels during acceleration. Similarly, the first term on the right-hand side of equation 14 represents the load acting on the rear wheels at static state or constant speed, and the second term represents the load resulting from the increase in weight of the rear wheels during acceleration. During braking, the acceleration AX has a negative value, and consequently, FXF and FX also have negative values. Thus, the direction of these forces changes to the opposite, as indicated by the red arrows. If the acceleration and forces acting in the longitudinal direction are defined in this way, equations 10, 11, and 12 can be applied in the same forms to acceleration and braking. The braking forces indicated by the red arrows, FXF and FXR, are negative numbers. By using the results of the analysis of the forces acting on the front wheel drive solid axle suspension links, which were examined in the previous video, E0082, Pitch Geometry Part 2, Front Wheel Drive, we can easily analyze the forces acting on the links during front wheel braking. For an efficient explanation, we will not consider the static vertical load acting in the static state or the constant speed, but will only consider the vertical load generated as a reaction to acceleration, delta FZF. All forces shown in the upper figure are forces generated by the front wheel drive force, FXF, and all forces shown in the lower figure are forces generated by the front wheel braking force, FXF. First, equation 15 can be derived from the equilibrium of the horizontal components of all forces acting on the front suspension links during front wheel drive in the upper figure. Equation 15 expresses that the driving force, FXF, must be in equilibrium with the resultant force of the horizontal component of the force F acting on the upper arm and the horizontal component of the force F acting on the lower arm. Next, equation 16 can be derived from the equilibrium regarding the vertical components of all forces acting on the front suspension links. Equation 16 expresses that the vertical component of the force F1 acting on the upper arm and the vertical component of the force F2 acting on the lower arm, which are generated as reactions to the driving force, FXF, must be in equilibrium with the ground reaction force, delta FZF, for the vertical dynamic load of the front suspension links. As mentioned, minus delta FZF does not include static load and is the ground reaction force for the vertical dynamic load transfer through the links generated by the driving force FXF. Next, equation 17 can be obtained from the moment equilibrium at point Q, where the extension of the lower arm intersects the straight line passing through the center of the front wheel and perpendicular to the ground, in the side view. The first term on the left side of equation 17 represents the moment generated by the driving force about point Q, and the second term represents the moment generated by the horizontal component of the upper arm about point Q. Solving equation 17 for F1 yields equation 18. Equation 18 expresses the force F1 acting on the upper arm as a function of the driving force Fxf. Substituting the F1 from equation 18 into equation 15 and solving for F2 yields equation 19. Equation 19 expresses the force F2 acting on the lower arm as a function of the driving force Fxf. Since the inputs for driving and braking are opposite, by reversing the signs of equations 15, 16, and 17, which represent the force and moment derived from front-wheel drive, we can obtain equations 20, 21, and 22, which represent the force and moment generated by front-wheel outboard braking. It is important to note here that, as explained earlier, the braking force, Fxf, is inherently negative, so its sign must not be changed. Solving equation 22 for F1 yields equation 23. Equation 23 expresses the force, F1, acting on the upper arm, as a function of the braking force, Fxf. Substituting F1 from equation 23 into equation 20, and solving for F2 yields equation 24. Equation 24 expresses the force F2, acting on the lower arm, as a function of the braking force, Fxf. Let us continue to examine the concept of the equivalent trailing arm. As explained in the previous video, E0087, pitch geometry part 1, rear solid axle, all suspension links, including wishbone suspension links, can be replaced with an equivalent trailing arm using a virtual reaction point at any given moment during pitching motion. For front-wheel braking, the front suspension links can also be replaced with an equivalent trailing arm using a virtual reaction point. By substituting equation 23, which represents the force F1 acting on the upper arm, and equation 24, which represents the force F2 acting on the lower arm, into equation 21 and rearranging for delta FZF, we obtain equation 25. Meanwhile, from the geometric arrangement of the suspension arms, the tangent value of the F1, the mounting angle of the upper arm relative to the horizontal plane, can be calculated as in equation 26, and the tangent value of the F2, the mounting angle of the lower arm relative to the horizontal plane, can be calculated as in equation 27. By substituting the derived equations 26 and 27 into equation 25, equation 28 can be obtained. From equation 28, it is shown that the ratio of the vertical dynamic load, delta FZF, to the braking force, Fxf, is equal to the ratio of the vertical component, E, to the horizontal component, D, of the straight line connecting the tire road contact point, A, and the virtual reaction point of the front suspension, SF. In equation 28, since the braking force Fxf is negative, the ground reaction force, delta FZF, generated through the link, is positive and increases the front wheel ground reaction force. This fact indicates that in front wheel braking, the upper and lower arms can be replaced by a single trailing arm rigidly connected to a solid axle, having the same virtual reaction point. As shown in equation 28, the vertical dynamic load, delta FZF, is the ground reaction force corresponding to the resultant force of the vertical component of the forces acting on all links when the braking force, Fxf, acts on the front wheel. As shown in the figure, during braking, if the virtual reaction point, SF, is behind the front wheel and above the ground, the vertical dynamic load, delta FZF, acts in a direction that increases the ground reaction force. This time, we will examine the link and spring forces when braking force is applied and determine their relationship with the total vertical dynamic load transfer. The figure on the left represents the total front wheel vertical reaction force, FZF, the vertical dynamic load transfer, front spring force, minus delta WZF, and the forces of the front links, minus delta FZF. Here, WSF represents the static vertical load acting on the front wheels. G represents the acceleration due to gravity, and AX represents the longitudinal acceleration. Minus delta WZF represents the vertical dynamic load compressing the front springs during braking. Here, delta WZF is the front spring force converted into a force acting along a line passing through the wheel center and perpendicular to the road surface. Minus delta FZF represents the vertical dynamic load compressing the front suspension links during braking. FZF represents the total vertical load on the front wheels. The total vertical force, FZF, acting on the front wheels can be expressed as equation 29 by adding the static vertical load, WSF, and the total vertical dynamic load. The second term on the right side of equation 29 represents the amount of vertical dynamic load transferred to the front wheels. The reason the sign of the vertical dynamic load in equation 29 is negative is that, since the acceleration AX is negative, it means that, when the braking force, FXF, is applied, the vertical load, FZF, on the front wheels increases by the amount of the vertical dynamic load. In a front suspension, with the braking wheels, the ground reaction force, which increases due to the amount of vertical dynamic load transferred, can be expressed as equation 2a, as the sum of the force compressing the spring, delta WZF, and the force compressing the links, delta FZF. Meanwhile, the braking force, FXF, can be expressed as equation 30 using the force on the links, delta FZF, derived from equation 28. Remember that FXF is negative in braking. What we aim to determine is the relationship between the front wheel braking force, dynamic force, and the vertical dynamic load acting on the front springs, delta WZF. Then, calculate the spring displacement, and from this, calculate the dive and pitch angles. For a front wheel braking vehicle, let's calculate the front spring displacement relative to the front wheel center. To do this, it is necessary to determine the relationship between the previously mentioned front wheel braking force FXF, the vertical dynamic load, and the vertical dynamic load acting on the front spring, delta WZF. By calculating the moment with respect to the virtual reaction point, SF, we obtain equation 31. In this equation, the reason the sign of the last term is negative is that the braking force, FXF, is negative and generates a positive moment with respect to the virtual reaction point SF. By rearranging equation 31 with respect to delta WZF, we obtain equation 32. Remember that, in equation 32, the acceleration AX and the braking force, FXF, are negative. Meanwhile, the force acting perpendicularly to the front wheel center, delta WZF, can be expressed as equation 33 using the front suspension wheel rate and the spring vertical displacement relative to the front wheel center. The vertical displacement of the spring relative to the wheel center refers to the displacement of the front spring measured vertically from the wheel center rather than along the actual spring axis. In equation 33, Kf represents the front wheel rate and delta F represents the displacement of the front spring measured along the vertical line passing through the front wheel center. The first term of equation 33 represents the vertical dynamic load of the entire vehicle when the acceleration is AX, and the second term represents the vertical component of the force acting on the front suspension links. Since no braking force acts on the rear wheels, the second term of equation 33 represents the force acting on the suspension links of the entire vehicle. From equation 33, it can be seen that the vertical dynamic load acting on the spring, delta WZF, is the difference between the vertical dynamic load transfer amount and the link force. Furthermore, from equation 33, it can be seen that if the vertical dynamic load of the entire vehicle is greater than the force acting on the links in absolute value, the spring force, Kf delta F, is positive, indicating that it acts in the direction of increasing the front wheel vertical load. Delta F has a positive value at the bump and a negative value at the rebound. Let us continue to determine the condition where dive becomes zero. When braking force is applied to the vehicle, if no vertical dynamic load is applied to the front suspension springs, the dive becomes zero. Furthermore, by calculating the spring displacements of the front and rear wheels relative to a line passing vertically through the wheel centers, we can determine the condition that makes the pitch angle zero when braking force is generated in the front outboard brake. The front spring displacement relative to the line passing vertically through the front wheel centers was calculated using equation 33, and the rear spring displacement relative to the line passing vertically through the rear wheel centers can also be calculated from equation 35 using the previously calculated vertical dynamic load of the rear springs, delta WZR. Here, delta WZR is the rear spring force, converted into a force acting along a line passing through the rear wheel centers and perpendicular to the road surface. In equation 35, Kr represents the rear wheel rate, and delta R represents the displacement of the rear springs, measured along the vertical line passing through the rear wheel centers. First, let's examine the conditions under which the dive becomes zero in a front wheel braking vehicle. From equation 33, we can obtain the geometric conditions of the suspension where the dive becomes zero. For the dive to be zero, the force acting on the front spring must be zero, so equation 36 must be satisfied. Therefore, equation 37 can be obtained from equation 33. Since the braking force, Fxf, can be expressed by equation 34, substituting Fxf from equation 34 into equation 37 and rearranging yields equation 38. For equation 38 to hold, the expression inside the parentheses must be zero, so we can obtain equation 39, which represents the conditions for the dive to be zero. Next, let's examine what geometry is required to make the dive zero. Based on the conditions expressed by equation 39, derived earlier, the geometry required to make the dive zero can be represented as shown in the figure here. Point G contains the center of gravity CG, and is the point where a horizontal line, parallel to the ground, intersects the vertical line, passing through the rear tire contact point B. Pitch geometry is analyzed based on the bicycle model. The forces acting on the left and right wheels combine into a single force at the vehicle's center longitudinal section. It is assumed that the vehicle's center of gravity is located at the vehicle's center longitudinal section. The green inclined line is the straight line connecting the front tire contact point A and point G. If a virtual reaction point SF exists on the inclined line between points A and G, then according to the property of triangle similarity, the ratio of H to L always has the same value as the ratio of E to D, thus satisfying equation 39. Therefore, if the virtual reaction point, SF, of the front suspension exists anywhere on the green straight line shown here, this vehicle will not dive during braking. The fact that dive does not occur does not mean that the pitch angle is zero. Let us examine the relationship between dive and pitch angle. Let's examine the relationship between dive and pitch angles and suspension geometry in this figure. First, let's look at the relationship between dive and pitch angle when braking force is applied and the dive becomes zero. A dive of 0 means that the vertical spring displacement relative to the front wheel center is 0, implying that the front ride height has not changed. However, as indicated by the orange line in the figure, even though the vertical spring displacement relative to the front wheel center is 0, the rear wheel displacement is not 0, and the rear ride height has increased. To make the pitch angle 0, the front ride height must be increased to the level of the rear, raising it to the level indicated by the gray line. To raise the front ride height to the rear level, the virtual reaction point, SF, must be increased. We will examine the reason for increasing the virtual reaction point, SF, from two perspectives: the forces acting through the springs and the forces acting through the suspension links. Let us examine how two kinds of forces transmitted through the spring and link change based on absolute values depending on the location of the virtual reaction point. Raising the virtual reaction point, SF, reduces the vertical dynamic load through the spring, delta WZF, while increasing the vertical dynamic load through the suspension links, delta FZF. Conversely, lowering the virtual reaction point increases the vertical dynamic load through the spring, delta WZF, while decreasing the vertical dynamic load through the suspension links, delta FZF. We will examine the physical implications of this through equations and figures. In this figure, the vertical axis represents the vertical height, E, of the virtual reaction point, and the horizontal axis represents the horizontal length, D, of the virtual reaction point. The origin of the coordinate axis is the front tire contact center, A. Rewriting equation 39, which represents zero dive, in terms of the independent variable, D, and the dependent variable, E, it can be expressed as equation 40. Equation 40 represents a straight line passing through the origin A with a slope of h divided by L. Therefore, this equation can be represented by the green straight line in the figure. In the yellow area of the figure, the pitch geometry can be expressed using inequality notation as in equation 41. In equation 41, as the height, EL, of the virtual reaction point, SF, increases, the absolute value of the force, delta FZF, on the suspension links, with the braking wheels increases. Since the total vertical dynamic load of the vehicle is constant, the absolute value of the spring force, delta WZF, decreases. In the yellow area, the spring force, delta WZF, and the force, delta FZF, on the suspension links, act in the same direction. Next, let's examine the pitch geometry in the area above the green straight line. In the region above the green line, pitch geometry can be expressed using inequality notation as in equation 42. In equation 42, as the height, EH, of the virtual reaction point, SF, increases, the magnitude of the force, FZF of the suspension links, with the braking wheels, increases in absolute value, exceeding the magnitude of the total vertical dynamic load of the vehicle. In this case, since the total vertical dynamic load of the vehicle is constant, the direction of action of the spring force, delta WZF, is reversed. As the virtual reaction point rises, the compressive force on the link increases, and the tensioning force on the spring increases. In the region above the green line, the spring force, delta WZF, and the force of the suspension links, delta FZF, act in different directions. For this reason, if the virtual reaction point is in the region above the green line, a tensioning force acts on the spring, increasing the front ride height more than in the steady state, and if the virtual reaction point is in the light yellow region between the green line and the ground, a compressive force acts on the spring, decreasing the front ride height less than in the steady state. Meanwhile, the total vertical dynamic load transfer of the vehicle, calculated using Newton's second law, represents the load transfer from the rear wheels to the front wheels and is independent of the position of the virtual reaction point, SF. The role of the virtual reaction point is to determine the ratio of load transfer transmitted through the springs to load transfer transmitted through the suspension links. Once this ratio is determined, the dive and pitch angles are determined. Let's summarize the relationship between link force, spring force, and ride height. To calculate the dive and pitch angles, the first step is to calculate the force, delta FZF, which is generated in the front suspension link containing the brake wheel. Once delta FZF is known, the spring force and displacement can be determined from equation 2, and the ride height and pitch angle can be calculated. When the suspension geometry is determined, the magnitude and direction of the resultant force of the links, delta FZF, are determined. Let's examine how delta FZF changes depending on the suspension geometry. Equation 30, derived earlier, expresses the braking force, Fxf, as a function of delta FZF, the ground reaction force, against the vertical dynamic load generated by the influence of the suspension geometry. Rearranging equation 30 for the vertical dynamic load, delta FZF, yields equation 43. In equation 43, since the braking force, Fxf, is negative, the ground reaction force for the vertical dynamic load, delta FZF, is positive. As shown in equation 43, the absolute value of the ground reaction force for the vertical dynamic load, delta FZF, which appears through the front suspension links during braking, increases as the ratio of E to D increases. If the absolute value of the force on the suspension links minus delta FZF increases, the force acting on the suspension links increases. From equation 2, if the braking deceleration, AX, is constant, the amount of vertical dynamic load transferred is constant. Therefore, if the force acting on the suspension links increases in absolute values, the force acting on the spring decreases, and the front ride height decreases less. If the virtual reaction point rises higher and is located in the region above the dive zero line, the vertical dynamic load acting on the spring changes from compression to tension, and the front ride height increases compared to the steady state. We will determine the conditions under which the pitch angle becomes zero by analyzing the forces generated on the springs and links, which vary depending on the suspension geometry. For the sake of convenience, we will assume that the front and rear suspension wheel rates are the same. Cases where these wheel rates differ will be explained later as we derive the formulas. In the suspension geometry of a typical commercially available vehicle, when braking force is applied, the force acting on the links acts vertically downward to compress the links, and the force acting on the springs also acts vertically downward to compress the springs. The sum of these two forces represents the total vertical dynamic load transfer. Meanwhile, zero dive means that the front spring displacement is zero, implying that the front ride height has not changed. However, as indicated by the orange line in the figure, even if the front spring displacement is zero, the rear spring displacement is not zero, and the rear ride height has increased. To make the pitch angle zero, the front ride height must be increased to the level of the rear, raising it to the level indicated by the grey line. To raise the front ride height to the rear level, the virtual reaction point, SF, must be raised. Raising the virtual reaction point, SF, increases the amount of dynamic load transferred vertically downward through the front suspension links, delta FZF. Conversely, the amount of vertical dynamic load transferred through the springs, delta WZF, decreases by the same amount that delta FZF increases. To be more precise, in absolute values, the vertical dynamic load compressing the springs, delta WZF, decreases by the same amount that the vertical dynamic load compressing the links, delta FZF, increases. If the height, E, of the virtual reaction point, SF, lies on the straight line connecting points A and G, no vertical dynamic load acts on the springs, and all vertical dynamic load transfer occurs through the suspension links. Since no vertical dynamic load acts on the springs, the dive becomes zero. However, since the rear ride height is still higher than the front ride height, the pitch angle is not zero. In the case of front wheel braking, if the height, E, of the virtual reaction point, SF, lies above the line connecting points A and G, the force acting through the front spring during braking becomes smaller than the force acting on the spring in the steady state. Consequently, the force acting on the spring acts vertically upward to tension the spring, causing the front ride height to increase while the rear ride height remains unchanged. As the virtual reaction point, SF, rises, the force attempting to tension the spring increases and the front ride height increases. As the force attempting to tension the spring increases, the amount of vertical dynamic load transfer to compress the front suspension links also increases. By utilizing this fact, we can find the location of the virtual reaction point that increases the front ride height while making the pitch angle zero. Keeping this in mind, let us examine the pitch angle. Let's calculate the pitch angle during braking. By determining the wheel displacements of the front and rear wheels, we can calculate the pitch angle when braking force is applied. The front spring displacement was previously calculated using equation 33, and the rear spring displacement could also be calculated from equation 35 using the previously determined vertical dynamic load of the rear spring, delta WZR. In equation 35, Kr represents the rear wheel rate, and delta R represents the rear spring displacement measured along the vertical line passing through the center of the rear wheel. When the pitch angle, phi p, is small, an approximation can be used in which the tangent, phi p, is equal to phi p. Here, phi p is in radians. After rearranging equation 33 for the front spring displacement, delta F, and equation 35 for the rear spring displacement, delta R, substituting these two displacement values into the second equation of equation 44, the pitch angle, phi p, when braking force is applied, can be obtained, as shown in the third equation of equation 44. Here, the spring displacement has a positive value at the bump and a negative value at the rebound. Rearranging equation 44, the pitch angle, phi p, can be expressed as equation 45. As expected, the pitch angle, phi p, expressed by equation 45 indicates that it can be expressed as a function of acceleration, mass, front and rear wheel rates, and the geometry of the front suspension link. Let us examine the meaning of equation 45 in detail. Let's determine the condition for the pitch angle to become zero. In equation 45 for the pitch angle, phi p, which was calculated earlier, if a braking force is applied and the braking deceleration, AX, is not zero, the condition for the pitch angle phi p to become zero is that the sum of the terms inside the parentheses in equation 45 becomes zero. Therefore, from equation 45, the condition for a zero pitch angle can be expressed as equation 46. By rearranging equation 46 for E over D, we obtain equation 47. The first term on the right side of equation 47 represents the anti-dive condition of equation 39, which was calculated earlier. As previously explained, in general suspension geometry, the condition for zero dive is not the same as the condition for the pitch angle to become zero. From equation 47, if the rear suspension wheel rate has a significantly larger value compared to the front suspension wheel rate, the second term of equation 47 can be ignored, so it can be seen that the conditions for zero dive and zero pitch angle are identical. Furthermore, equation 47 explains that if the difference between the front suspension wheel rate and the rear suspension wheel rate is not significant for the pitch angle to become zero, under the condition of zero dive, the height of the center of gravity must either decrease by nearly half or the value of E over D must nearly double. In equation 47, if the front wheel rate is equal to the rear wheel rate, the condition for a zero pitch angle can be expressed as equation 48. Let's verify the above explanation with a figure. Let's examine the geometry required to make the pitch angle zero using a figure. Based on the condition expressed by equation 47, derived earlier, the geometry required to make the pitch angle zero can be represented as shown in this figure. To make the explanation efficient, I will use equation 48, which assumes that the front wheel rate, Kf, and the rear wheel rate, Kr, are equal. In the figure, point S is the point where a horizontal line parallel to the ground, passing through point U, which is at twice the height of the center of gravity, Cg, intersects the vertical line, passing through the rear tire road contact point, B. To satisfy equation 48, the ratio of the height of twice the center of gravity to the wheelbase must be equal to the ratio of E to D. The line satisfying this condition can be represented by the blue straight line in the figure. The blue inclined line is the straight line connecting the front tire contact point A and point S. If a virtual reaction point, SF, exists on the inclined straight line between points A and S, then according to the property of triangle similarity, the ratio of 2H to L always has the same value as the ratio of E to D, thus satisfying equation 48. Therefore, if the virtual reaction point, SF, of the front suspension exists anywhere on the blue straight line shown here, the vehicle can maintain a zero pitch angle attitude during braking. As explained earlier, when front wheel braking force is applied, in order to maintain a zero pitch angle attitude, the front ride height must increase by the same amount as the rear ride height increases. Consequently, the final vehicle attitude with a zero pitch angle inevitably involves an increase in both front and rear ride heights, resulting in the attitude indicated by the gray line. In a front-wheel braking vehicle, raising the virtual reaction point increases the front ride height. Let's briefly summarize the pitch geometry during front-wheel braking. It is important to note that, regardless of where the virtual reaction point is located, the amount of vertical dynamic load transferred from the rear wheels to the front wheels remains unchanged once the acceleration AX is determined. By the amount of the load transfer, the front ground reaction force increases and the rear ground reaction force decreases. Using the previously explained di-zero coordinate system, the zero pitch angle condition can be expressed by equation 52, which represents the blue line. In the region below the blue line and above the green line, the pitch geometry can be expressed using an inequality as in equation 51. Similarly, in the region above the blue line, the pitch geometry can be expressed by inequality 53. If the virtual reaction point, SF, exists in the region between the green line and the road surface indicated by yellow shading, the spring force, delta WZF, acts as a compressive force on the spring, and the force on the suspension links, delta FZF, also acts as a compressive force on the links. This direction is the direction in which the spun mass moves downward. Ride height decreases at the front and increases at the rear compared to the steady state. If the virtual reaction point, SF, exists on the green line, the spring force, delta WZF, becomes zero, the spring displacement is zero, and delta FZF acts in the direction of compressing the suspension links. In this case, The absolute magnitude of the force, delta FZF, is equal to the load transfer of the vehicle. Since there is no change in front ride height, this case is dive 0. Ride height remains unchanged at the front and increases at the rear compared to the steady state. If the virtual reaction point, SF, exists in the area between the blue and green lines indicated by the blue shading, the spring force, delta WZF, acts as a tensioning force on the spring, and in absolute values, delta FZF, compresses the suspension links with a force greater than delta WZF. Ride height increases at both the front and rear compared to the steady state, but the increase in ride height is greater at the rear than at the front. If the virtual reaction point, SF, exists on the blue line, the absolute value of the spring force, delta WZF, becomes half the force of the suspension links and acts as a tensioning force on the spring. Delta FZF acts in the direction of compressing the suspension links. In this case, the force, delta FZF, becomes twice the load transfer of the vehicle in the absolute value. As the ride height increases at the front to the rear level, the pitch angle becomes 0. If the virtual reaction point, SF, exists in the region above the blue line, the force compressing the link is greater than the force tensioning the spring, and in absolute values, the difference between these two forces is equal to the load transfer amount. Additionally, compared to the steady state, the front ride height increases more than the rear ride height. If the virtual reaction point is located on the road surface, the height of the virtual reaction point, E, is 0, so the link force is 0, and delta WZF acts as a force compressing the spring. In this case, the decrease in front ride height is equal in magnitude to the increase in rear ride height. If the virtual reaction point is located below the road surface, the height of the virtual reaction point, E, is negative, and as shown in equation 54, delta FZF becomes positive, acting as a force tensioning the link. The force compressing the spring is greater than the force tensioning the link, and in absolute values, the difference between these two forces is equal to the load transfer amount. In this case, the decrease in front ride height is greater than the increase in rear ride height. Let's find the answer to the quiz. In a front-wheel braking vehicle, which statement is correct when the virtual reaction point is located between the dive 0 line and the pitch angle 0 line? Number 1. In absolute value, the link force is larger than the spring force. Number 2. In absolute value, the link force and the spring force are not equal. Number 3. The front ride height becomes larger than in the static state. Number 4. The rear ride height becomes larger than in the static state. Number 5. The front ride height is smaller than the rear ride height. Number 6. The front ride height is smaller than the rear ride height. The correct answer is number 6. Let me summarize the content of this video. I explained the pitch geometry of front-wheel outboard braking vehicles. Dive is the phenomenon where the front of a vehicle drops downward when braking with the front wheels. Because the braking force generated horizontally at the tire contact surface acts below the center of gravity, the front of the vehicle body naturally drops while the rear lifts. Anti-dive geometry refers to the geometric arrangement of the front suspension links to prevent the front of the vehicle from dropping. I also explained the location of the virtual reaction point and vertical load transfer. Raising the virtual reaction point reduces the vertical dynamic load through the springs and increases the vertical dynamic load through the suspension links. Lowering the virtual reaction point increases the vertical dynamic load through the springs and decreases the vertical dynamic load through the suspension links. I explained the dive and pitch angles when front braking force is applied. Zero dive means that the front spring displacement is 0, implying that the front ride height has not changed. If the dive is 0, the front spring displacement is 0, but the rear spring displacement increases. I explained how to achieve a zero pitch angle. To achieve a zero pitch angle, the front ride height must be raised to the level of the rear ride height. To do this, the virtual reaction point must be raised. Raising the front virtual reaction point increases the tensioning force of the spring, thereby increasing the front ride height. I explained how to achieve a zero pitch angle when the front and rear suspension wheel rates are equal. Under zero dive conditions, one must either lower the height of the center of gravity by half or double the height of the virtual reaction point. I explained the conditions under which the pitch angle becomes zero. As the rear ride height increases, the front ride height must also increase accordingly. Therefore, the front and rear ride heights must both increase by the same amount. The physical principles regarding the position of the virtual reaction point in front-wheel braking vehicles have been explained. If we denote the ratio of the vertical position to the horizontal position of the virtual reaction point relative to the braking tire's road contact center as SR, and the ratio of the center of gravity height to the wheelbase as CR, the change in ride height can be determined from these. If SR is less than 0, the front ride height decrease is greater than the rear ride height increase. If SR is 0, the front ride height decrease is equal to the rear ride height increase. If SR is greater than 0 and less than CR, the front ride height decrease is less than rear ride height increase. If SR is equal to CR, the ride height remains unchanged at the front, but increases at the rear. In this case, the dive becomes 0. If SR is less than 2CR and greater than CR, the ride height increases in both the front and rear, but the rear increase is greater. If SR is equal to 2CR, the ride height increases by the same amount at the front and rear, and the pitch angle is 0. If SR is greater than 2CR, the ride height increases in both the front and rear, but the increase in the front is greater. The relationship between the vertical dynamic load transfer and the virtual reaction point has been explained. In front-wheel braking, the vehicle's total vertical dynamic load is the amount of load transferred from the rear wheels to the front wheels. The amount of load transfer of the vehicle is independent of the location of the virtual reaction point. The role of the virtual reaction point is to determine the ratio of the load transfer amounts through the springs and suspension links. Once the load transfer ratio is determined, the dive and pitch angles are determined. The dive and pitch angles can be adjusted using the location of the virtual reaction point. If you watch the previous videos, you can learn about various fields of vehicle dynamics and enjoy a more in-depth understanding of future videos. In my recent video, E0087 Pitch Geometry Part 5, I explained the suspension geometry that makes the squat 0 and the suspension geometry that makes the pitch angle 0 when accelerating an independent rear-wheel drive vehicle, and explained the vehicle attitude according to the pitch angle determined by 7 positions of the virtual reaction point. In a recent video, E0086 Pitch Geometry Part 6, the lift and pitch angles of a front-wheel drive vehicle with a front independent suspension system were explained, and how the lift and pitch angles change depending on the 7 positions of the virtual reaction point. Additionally, it was explained that the front ride height can decrease depending on the position of the virtual reaction point, even during acceleration. The next video will be Pitch Geometry Part 8. I will explain how to analyze rise in the pitch motion for the outboard rear wheel brakes. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to see new videos. So, what are you waiting for? See you at next videos. Goodbye, guys.